Dear viewers, I welcome you all for this continued session in infrared spectroscopy where in this particular session we will be discussing on the factors that influence the vibrational frequencies. And just to recollect, in the previous sessions we have discussed more about the fundamental vibrational frequencies and how do we calculate theoretically the vibrational frequencies of any given molecules, and what are the number of vibrational frequencies, or how do we calculate the vibrational frequencies associated with any given molecule by knowing its fundamental modes of vibrations for linear and non-linear molecules. And we have discussed further the kind of vibrations any molecule possesses. So in this particular session I would like to discuss with respect to the factors that influence the vibrational frequency of any given molecule. And myself, Dr. Girish Hampanava, Assistant Professor, KLE College of Pharmacy, Vidyanagar, Hubli, would like to engage in this particular session with respect to these factors that influence the vibrational frequencies. So coming to the factors that actually influence the vibrational frequency of any given molecule. So far we have discussed in the previous session that if we have any molecule, theoretically by using Hooke's law we can calculate the vibrational frequency of any bond which is attached to two different atoms. So that is how we calculate the probable absorption or the probable wave number of a particular group, that is two atoms, for example, which is attached by a particular bond. If you are to calculate the vibrational frequency of that particular bond, then we can use Hooke's law, wherein which we calculate the bond strength, and after knowing the atomic masses we calculate the reduced atomic masses. Then theoretically it is possible to calculate the wave number of a given molecule. But what happens is this theoretically calculated wave number does not actually experimentally happen. That is because we have discussed in the previous session that most of the vibrational frequencies sometimes they fall out of the region under investigation, and sometimes they are rather too weak to be observed as a peak, and sometimes there is no change in the dipole moment, that's why there is no peak visible. And also we discussed with respect to the combination bands, difference bands, and overtones in the previous sessions. So because of those reasons, the theoretically calculated wave number is practically sometimes not seen. So there are some other reasons why this theoretically calculated wave numbers are possibly not seen, is because there are some things which influence the vibrational frequencies. So in this particular session we will go on and discuss what are the factors that actually influence the expected vibrational frequencies and what leads them to shift from the expected regions. So I mean to say the calculated vibrational frequencies will never match the experimental value, because the vibrational frequency of each group, it gets rather influenced by the structure of the molecule in the immediate neighborhood of the bond. So if there is any molecule or the atom which is attached to a particular atom of interest, which in turn is attached to a bond, so that particular atom which is attached to the atom of interest, if it is influencing the atom of interest by some means, then the vibrational frequency of the atom of interest which is connected to a particular bond, and the vibrational frequency of that particular bond gets disturbed. And possibly we can categorize the several factors which will rather influence the vibrational frequencies under several headings. The first being the coupled vibration and Fermi resonance. The second is the electronic effects. The third one is conjugation. The fourth one is bond angle. The fifth one is hybridization. And the sixth one is the hydrogen bonding. So all of these factors in some way or the other way will lead to the shifting of the vibrational frequencies from the expected values. So in this particular session I would like to go through all of these individual factors which will influence the vibrational frequencies and how they shift the vibrational frequency from an expected region to some other region. So first, coming to the coupled vibrations. and Fermi resonance. I will go through all these factors individually. So first I would like to take up the coupled vibrations and Fermi resonance. So coupled vibrations, what we mean by coupling of vibrations. We have also discussed this in the previous episode, where if there is a coupling between the two similar atoms which are attached by a common atom, if there is a coupling, then there leads to two different peaks which arise out of these coupling vibrations. So the same thing I would like to explain in detail here. So what we mean by coupled vibrations. For example, if you have an isolated CH bond, we expect one stretching absorbance theoretically. So that does not happen, because in case of methylene, if you see, we expect rather two absorbances, that is symmetric and asymmetric, and we call them as the coupled vibrations. So we have discussed this symmetric and asymmetric stretch. Symmetric is if this carbon is attached to two different hydrogens, which I have represented here. If these two hydrogens are moving away and towards this carbon simultaneously, then we call it as a symmetric stretch. If one hydrogen is moving away and the other hydrogen atom is moving towards this carbon, then we call that as asymmetric stretch. If that is the case, then we call it as the coupling of vibrations, and they fall into two different types. They are the symmetric and asymmetric, and thus we call them as the coupled vibrations. So if there is a coupling of vibrations, always it is a rule of thumb that asymmetric vibrations usually fall at the higher wave number, or they appear at the higher wave number when compared to the symmetric vibrations. And this coupled vibrations, or these are known as coupled vibrations because the vibrations usually occur at different frequencies than that required for the isolated CH stretching. So I usually expect one stretching vibration for this isolated CH bond, but rather I get two different peaks at two different frequencies, where there is where there are two different peaks, which are possibly because of this coupling of CH stretching vibrations, and we call them as symmetric and asymmetric stretch. So I have an example here. As I was talking about the CH stretch in this particular slide, I have taken this anhydride molecule, where I also find two different kinds of symmetric, I mean to say, there is a vibrational coupling that happens between these two carbonyl groups, wherein which they are categorized as symmetric and asymmetric stretch, and that symmetric and asymmetric stretch is a sort of vibrational coupling that happens in this particular acid anhydride molecule. So this acid anhydride has two carbonyl stretching absorbances between 1850 to 1800 and 1790 to 1745 centimeter inverse, which is nothing but the wave number. So I expect two vibrational frequencies out of these two carbonyl groups which are present in this acid anhydride, and that is possibly because of asymmetric and symmetric stretch. I also mentioned in the previous slide, always it is the asymmetric stretch which happens at the higher wave number. So we have we have this particular representation here, where it is a sort of asymmetric stretch. You can see the carbonyl group, the oxygen is moving towards the carbon here, whereas in this particular carbonyl group, the oxygen is moving away from this particular carbon. So this becomes an asymmetric stretch, whereas there is symmetry in the movement of in these two oxygen atoms with respect to these two carbon atoms. So this is a symmetric stretch, and this is an asymmetric stretch that is happening because of vibrational coupling in this acid anhydride molecule. So the asymmetric stretch has around 1800, the absorption at 1800, whereas the symmetric has the absorption around 1760 wave number. So I have represented an example here, which is an acid anhydride derivative, where there are two peaks, which is possibly because of the vibrational coupling. If there was no coupling, I would have expected only one peak here. Since there is a vibrational coupling and I am getting two symmetric and I mean to say two peaks, one because of asymmetric and the other one is because of symmetric stretch, stretching vibrations. So it is always the asymmetric stretch at the higher wave number, whereas the symmetric stretch at the lower wave number. So the coupling between occurs between the carbonyl groups, which are indirectly linked through one common atom. So I mentioned previously that coupling usually happens between the two molecules which are connected to a common atom. So these two molecules, that I mean to say, these two carbonyl groups are linked to a common atom, and coupling usually happens when two molecules or two atoms are connected to one common atom. And this oxygen bond and this interaction um, of this carbon and oxygen through this common oxygen bond gives a slight double bond character in the carbon oxygen bond. So because of this double bond character, the bond this because of this resonance which happens between this carbon and oxygen, this bond slightly assumes a double bond character. So that was with respect to the coupled vibrations which I have represented here: the symmetric at the higher wave number, the asymmetric at the higher wave number, and the symmetric vibration at the lower wave number. After this coupled vibrations, we have something called as Fermi resonance. And before I go to this Fermi resonance, I would like to recollect what we discussed as an overtone in the previous episode. Overtone is nothing but if a vibrational frequency is happening at x, if there is another peak corresponding to this particular vibrational frequency at 2x, if there is one more small peak, we call that peak as overtone peak. If there is a fundamental peak at x value, at 2 times x, there is a small peak which we call it as an overtone. That is a sort of combination different bands. When we were discussing combination bands and the difference bands and the overtones, we discussed this particular overtone. So Fermi resonance is something where if the energy of overtone level coincides with the fundamental mode of another vibration, if one fundamental mode vibration of one set is coinciding with the overtone of the other set, then we call that as a Fermi resonance. So for example, I have taken as an aldehyde here. I have taken the Fermi resonance that is happening in aldehydes, in which the CH stretching absorption usually appears as a doublet at 2820 and 2720. This CH stretch usually happens as a doublet around 2800 because of the interaction of CH stretching and the overtone of the CH deformation. I mean to say, if you see this particular image, the CH stretch usually happens at 2800, and there is also the CH bend which happens, which falls in the fingerprint region of this particular spectra, and that fingerprint region is around the 1400. The bending vibrations of this CH is usually seen at 1400, and there is a overtone of this bending vibration at 2800. That's why we see two different peaks at 2800 as a doublet. So this is what we call as Fermi resonance. I would like to repeat this whole discussion once again. The Fermi resonance is nothing but the coincidence or the merging of the fundamental mode of one vibration with the overtone of the other vibration. So the first vibration I expect is the CH stretch at 2800, and there is also CH bend which is happening at 1400, and the 1400, the bending vibration give rise to an overtone at 2800. That's why at 2800 I expect two peaks which appears as a doublet, and there are two peaks which are happening at 20 and 2720. I think you can see this 2820 and 2720, which is because of the interaction of the CH stretching, which is a fundamental vibration, with the overtone of CH deformation, which is nothing but the bending. You can see the CH bend is happening here, and an overtone of this CH bend is happening here. So it is the merging of the fundamental and the overtone of the CH bond which happens as a doublet. We call this as Fermi resonance. So after this, we would like to come to the next factor that influences the vibrational frequencies. the second factor that influence the vibrational frequency is the electronic effects in general. So the electronic effects can be categorized into three subtypes. The first one is the inductive effect, the second one is the mesomeric effect, the third one is the field effect. In all of these three effects, there is an involvement of the electrons, and thus we categorize them as the electronic effects in common. So coming to the first one, which is the inductive effect. In this particular inductive effect, the frequency shifts. Because of this inductive effect, the frequency usually shifts from the normal position, and due to the electronic effects, the force constant, very important, the force constant or the bond strength changes, and thus the frequency shifts from the normal position. As we have seen the Hooke's law, where we are calculating the frequency, which is directly proportional to the bond strength divided by the reduced mass or the reduced atomic masses. So if the force constant or the bond strength is getting altered, then the frequency of vibration will also definitely get affected because of that. So if you change the electronic configuration of the molecule across the bond, then the force constant of that particular bond or the bond strength of that particular bond changes, which leads to the shift of frequency from the expected values. And introduction of an alkyl group in particular causes the positive inductive effect, whereas introduction of any electronegative atoms causes negative inductive effect. And the positive inductive effect, if there is a positive inductive effect, the absorption takes place at the lower wave number, and if there is a negative inductive effect, the absorbance takes at an increased wave number. In the next slide, I will make it more simplified, where we have an example for positive as well as negative inductive effect. And we should not confuse this inductive effect with the mesomeric effect, whereas the inductive effect is purely because of the electronegativity of the atoms, whereas the mesomeric effect is the result of the pi orbital overlap, which is nothing but the resonance. And we should not but both being the electronic effects, the inductive effect should not be confused with the mesomeric effect. So I have summarized the effect of inductive effect on a given vibrational frequency. So if I have a positive inductive effect, there is an atom which is bringing about this positive inductive effect. That particular atom is deficient of electron, and if that is deficit of electron, it tries to draw an electron from the bond. So if the bond is giving that electron for that electron deficient atom, then the bond length increases and the force constant definitely decreases. And if the force constant decreases, according to Hooke's law, if the numerator decreases, then the frequency value will also decrease. So the frequency, if it is decreasing, then the absorbance will happen always at the lower wave numbers. So for example, the electron deficient atoms like alkyl groups, which are deficient in electron, if I attach alkyl groups, more and more alkyl group, I will see more and more positive inductive effect. So if it is more and more positive inductive effect, the absorbance value will tend to go towards a very lower wave numbers. And similarly, the vice versa, negative inductive effect is nothing but if you attach an electron rich molecule to an atom which is attached to a bond whose vibrational frequency is under study. If you increase the electron richness of the atom, then what happens? This electron rich or electronegative atoms will be having more and more tendency to draw the electrons, and thus the bond length will decrease, because the electrons which are present in the bond are taken up by this electron or this electronegative atoms, and the force constant will increase. If the force constant is increasing, the frequency will also increase, and the absorbance will tend to happen at the higher wave number. So I have an examples for negative inductive effect, which are nothing but the chlorine, bromine, iodine, OH, etc. So the electron rich and the electron deficient is the thing which brings about the positive and the negative inductive effect. So I have an example here. Yeah, for inductive effects. For positive inductive effect, I need to add more and more alkyl groups. If you see, I have an aldehyde or formaldehyde as an example, where I am studying the carbonyl stretching absorptions. In this particular formaldehyde, the carbonyl absorption is around 1750, and in the acetaldehyde I have added an alkyl group to this aldehyde group. You can see it was initially H. I have added CH3, and in the later case I have added two CH3s, which is nothing but the acetone. And if you see in general, the carbonyl frequencies in all these three compared to aldehyde, these rest, the absorption frequencies have gone down. I mean to say, the absorption frequency has gone to a lower wave number because I am increasing the positive inductive effect in this particular set of molecules. And for example, negative inductive effect, I have taken the same acetone here, and what I try to do is I add the electronegative atoms like chloroacetone, one electronegative, and dichloroacetone. I have added two electronegative atoms to this acetone. So I can see the carbonyl stretching frequency. It was 1750 for acetone. As I started adding electronegative atoms, I started adding the negative inductive effect, so the vibrational frequency started to increase just because the bond strength started to increase because I added the electron rich atoms. So that is how the positive and the negative inductive effect will affect the vibrational frequencies of any given molecule. And this was the examples or the set of the examples which were depicting the inductive effects. After this inductive effect, there is a second electronic effect, which is the mesomeric effect. As I mentioned, it should not be confused with the inductive effect, which is a sort of resonance which is bringing about the change in the vibrational frequencies. And this mesomeric effect or the resonance effect, it causes the lengthening or weakening of the bonds, leading to lowering of the absorption frequencies. So whenever there is a resonance or the mesomeric effect, it usually causes the lengthening of the bond. And if there is the lengthening of the bond strength usually goes down. So if the bond strength or if the numerator is going down, then the vibrational frequency also drops. And I have an example here. This is an example which I will be discussing very much in the next slide. As nitrogen atom is less electronegative than compared to the oxygen atom, the electron pair on the nitrogen atom in the amide is more liable and participates more in the conjugation. So there is a pair of electron which is present on the nitrogen, and since nitrogen is less electronegative when compared to oxygen, this pair of electron is more liable and is more available to participate in the conjugation. So I would like to bring your attention here where I am trying to show the mesomeric effect, wherein which, as I mentioned, this nitrogen is less electronegative when compared to the oxygen. The lone pair of electrons which are available on this nitrogen are available for the conjugation. So what happens is this set of electrons go in conjugation with this carbon, and what happens as an end result, this increases the conjugation. And if there is an increase in the conjugation, as you can see, there is a double bond here, and there is the loss of electrons across this particular carbonyl bond. And what happens, there is increase in the conjugation, and as a result what happens is there is a lower vibrational frequency for this particular carbonyl group. As a result, these amides will tend to show the absorption at a very low vibrational frequencies when compared to the esters. And if you see, instead of nitrogen, here we have an oxygen which is more electronegative, and we have seen these electronegative atoms will bring about the negative inductive effect here, as we have seen, and because of that negative inductive effect we have the absorbance at higher wave number. So this inductive effect and the mesomeric effect are sort of hand in hand concepts, where they actually potentiate the reason for appearance of these vibrational frequencies at two different regions for esters and amides. And this particular set of electrons on this particular electronegative atom, they are or this oxygen atom is since more electronegative when compared to nitrogen atom. It brings about the negative inductive effect, which I have mentioned it here in the inductive effect. And because it is an electron rich, the bond strength also increases and the vibrational frequency also increases. That's the reason the ester, the carbonyl frequency or the absorption frequency happens at a higher wave number when compared to the amide carbonyl frequency, which happens at the lower wave number. You can see it is 1690 for amide and 1735 for this particular carbonyl which I am discussing. And all these vibrational frequencies are for the carbonyl groups which are present in all of these chemical class of compounds. So that is how the carbonyl frequencies gets disturbed or shifted from the normal expected position. That is because of this mesomeric effect or the inductive effect. The third electronic effect which we try to study is the field effect, and the reason for including this in the electronic effect is because again a lone pair of electrons that are present on an atom that influence, if it is showing the influence through space, and if it is changing the vibrational frequencies of this particular carbonyl or this particular C single bond C or this particular carbonyl functional group, then we call it as the field effect. If you see this carbonyl and this particular atom is not attached to a common atom, rather there are two different two atom distance between these two, and if this is the case, there is an effect through space. We call it as a steric effect, and also we call it as a field effect. And because of the field effects, if a lone pair of electrons are present on the ortho position of any given aromatic ring, that will influence the carbonyl absorption frequencies or the vibrational frequencies, and this we call it as the field effect. And after this, we have the third kind of factor which influences the vibrational frequency, that is the conjugation effect. I am discussing the three cases here where we are increasing the conjugation and we are taking some conformers and we are taking some unsaturations or alpha beta or increase in the unsaturation, and we are discussing all these three and understanding how the conjugation is affecting the vibrational frequencies. So as a rule of thumb, the conjugation will lower the wave number of absorbance of carbonyl group. The more conjugation, that is because I mentioned here this conjugation of the electrons or this lone pair of electrons on the nitrogen which are involved in the formation of the double bond, and that leads to a conjugation here. And anything that leads to conjugation, I can generalize this statement, will bring down the vibrational frequency. Based on that concept, I have taken this particular conjugation effect where conjugation lowers the wave number of absorbance of carbonyl stretch. More the more conjugation, lesser the wave number of absorbance. I have an example as acetone here, where I have tried to add a conjugation here by adding a double bond between these two carbon atoms. Here there is no conjugation and here there is one conjugation. So on increasing or on adding the conjugation, what happens? If you can see, the vibrational frequency is going to the lower wave number. Okay, the vibrational frequency of this carbonyl group and of this carbonyl group, where it was 1720 for this and it is 1705 for this carbonyl group. I mean to say, there is a drop in the vibrational frequency as I have increased the conjugation. Similarly, there is drop in the carbonyl frequency as there is a resonance, mesomeric effect. I have increased the conjugation. We can also call it as the mesomeric effect. If there is so, then the carbonyl frequency is still more dropping to 1700 wave number. So this is how when I increase the conjugation, what happens to the absorption of carbonyl group. Similarly, I have an increase in the conjugations in this set of examples here, one double bond and two double bonds and three double bonds. If I have a case where I have a carbonyl group on this particular ring, then what would be the vibrational or the absorption of that particular C double bond O? It would have been 1645, 1620, 1600. So there is a drop in the vibrational frequencies of those particular carbonyl groups. So that was the case. If I increased the conjugation, there was a drop in the vibrational frequency, and the vibrational frequency was happening at the lower wave number. So, and in the second case, I have tried to compare the conformers, and I have a generalized statement here where the cis conformers absorbs higher frequency than the trans conformer. That is because this cis conformer shows some dipole moment which has around 0.3 d, and upon stretching the double bond, the dipole moment will change. And since it is responding, because as we have seen in the very basic understanding of this or the very basic requirement, there should be change in the dipole moment for a molecule to show IR absorption. And since this cis 2 butene is showing the dipole moment or change in the dipole moment, we would expect an IR peak for this C double bond C stretch. So since there is a dipole moment, this cis 2 butene will show some IR absorption. Whereas when we come to this trans 2 butene, this trans 2 butene does not have any dipole moment. If there is no dipole moment, then possibly there is no question of this molecule showing any IR absorption. So we would not expect to see any IR peak for C double bond C stretch in this particular trans 2 butene. So cis conformers, it shows absorption, and I have taken a particular example where only the cis form shows absorption, whereas the trans form do not show any absorbance because there is no change in the dipole moment. And the dipole moment, the change in the dipole moment is a prime requirement for a molecule to show an IR absorption. And this was about the cis and trans conformers. And with respect to the unsaturation, as I talked in this, increase in conjugation or increase in a sort of unsaturation will leads to drop in the absorption frequency of the carbonyl functionality. And if imagine these molecules or these functionalities to be attached to a molecule which has the carbonyl functional group, and if there is only one double bond, I have a vibrational frequency of 1650 for that carbonyl group. And if I have two double bonds or conjugated double bonds, then I would like or I mean to have we end up having a carbonyl stretching vibrational frequency of 1610 for that particular molecule. So any change or any increase in the conjugation would drop or lower the wave number of absorbance of carbonyl stretch. And as I mentioned, the cis conformers show higher frequency, or in this particular set of example, only the cis conformer shows the IR absorption for this C double bond C, whereas the trans conformer do not show because it does not produce any change in the dipole. That's why there is no IR peak which is visible for trans 2 butene. After this, the next factor that influences is the bond angle. So increase in the ring strain, okay, I mean to say, if you see this ring and this ring and this ring, there is increase in the ring strain or decrease in the bond angle. If there is decrease in the bond angle or if there is increase in the ring strain, then what happens is it leads to the increased S character in the bond. I will discuss this, what we mean by S character, in the next slide, where in which if there is increased S character, then the bond tends to become shorter and shorter. If it is becoming shorter, then it becomes strengthened, and if it is becoming strengthened, then the bond strength increases. Then thus, according to Hooke's law, the wave number increases. So if I talk about with respect to this carbonyl functionality which is attached to all of these ring molecules, if the ring strain is increasing, then the carbonyl stretching frequency also increases with respect to the ring strain. Or if it is reducing, or if the bond angle is reducing below 120 degrees, it leads to the increase in the S character. And increase in the S character would actually contribute for the shortening of the bond and strengthening of the bond, and that's why if the bond strength is increasing, then the wave number also increases. So these are set of the examples for C double bond O and C double bond C states. And the highest carbonyl frequencies arise in the strained cyclobutanes. This can be explained in terms of bond angle strains, and if bond angle is reduced below 120, then the CO stretching is reduced and occurs at a higher frequency, and if the bond angle is pushed outwards 120, then it leads to increase in the bond length, and if there is increase in the bond length, the CO stretching happens at the lower frequencies. So that is how we can substantiate this bond angle to the vibrational frequency. With respect to the hybridization, which is the next factor which influences the vibrational frequency, as S character increases, there is an increase in the wave number. Okay, as S character increases, there is an increase in the wave number. So what do we mean by S character? S character is a contribution of a sigma type bond in a hybridization process. So what is whatever there is the contribution of the sigma type bond in the hybridization, we call that contribution as a S character. The more the S character a bond has, the stronger and shorter the bond is. So an sp-sp bond is the strongest and sp-sp3 bond is the weakest. sp3-sp3 bond is the weakest bond. So if you see this particular chart, I have represented 3 cases where there are 3 different bonds. In the first case it is the sp, in the second case it is sp2, and in the third case it is sp3 hybridized orbitals. So I will be talking about with respect to this CH stretching in all these 3 cases. Why I am talking with this CH3 is because this CH is because this carbon is attached to this carbon, which is linked by 3 triple bonds, and this carbon by double bonds, and this carbon by single bond. I am talking about this CH stretching frequencies. So these are the types of bonds. This is sp, and this is sp2, and this is sp3. And if you see the bond length here is 1.08 Armstrong, and in sp2 it is 1.10 Armstrong, and in sp3 it is 1.12 Armstrong. As you can see, as I go from sp to sp3, the bond length increases. Okay, that is the general observation what I am making. As the bond length increases, the strength decreases. That is a general statement what I am making. And as the bond length increases, the strength decreases, the vibrational frequency also decreases. Okay, so with respect to the S character also decreases as I move from sp to sp3. Okay, there is 50% S character in sp, 33% in sp2, 25% in sp3, and more the S character, there is increased wave number and there is increased bond strength, whereas the length is the smallest. That is what I am making as a general statement. Okay, so increased percentage S character leads to increased bond strength, decreased bond length, and increased wave number of absorption. That is the general observation what I am trying to draw here. And if the length is small, if you see the length is small compared to this, if length is small, the force constant is high, and then the absorption is also high. Okay, in general, the more the S character in the bond, stronger is the bond, and hence the absorption is happening at the higher frequency. This is what we understand by hybridization. Coming to the last point, which is the hydrogen bonding. Hydrogen bonding, what it does is hydrogen bonding, it lengthens. Hydrogen bonding involves the lengthening of the original OH bond. If there is a lengthening of the bond, if you see, if there is a lengthening of the bond, if you can, for in this particular example, as the bond length is increasing, the absorption frequency is decreasing. We are applying the same concept here. If there is hydrogen bonding, that involves the lengthening of the OH bond, original bond, hence weakening, thus lowering the stretching frequencies. If I am bringing about the hydrogen bonding, more and more hydrogen bonding, that leads to the lengthening of the bond, which leads to the lowering of the stretching vibrational frequency. So hydrogen bonding gives rise to lower frequency shift. That is what I have made as a general observation here. Stronger hydrogen bonding, greater shift towards a lower wave number from a normal value. Okay, so if there is more hydrogen bonding that is happening, then there is a shift of the wave number to the normal, shift of wave number to the lower wave numbers from the normal values. So it is by this process we can distinguish the two types of hydrogen bondings by IR technique. There are two types of hydrogen bondings that are possible. The first one is intermolecular, the second one is intramolecular. Intermolecular is between the molecules, intramolecular is within the molecule. And how can we distinguish? The intermolecular, if we observe the IR spectrum of these two, then the broad bands will be possible in the intermolecular hydrogen bonding, and they are dependent on the concentration. More the concentration, more broader the band is, lesser the concentration, lesser the intermolecular hydrogen bonding, and less broad the bands are. And they are usually sensitive to dilution. On dilution, the intensity of the band tends to decrease, and finally at some extent it will disappear, because since it is the intermolecular hydrogen bonding, on dilution these intermolecular hydrogen bonds are destroyed, and thus on dilution the intensity of these bands will tend to disappear or slow down and then disappear finally. And frequency difference between the free and associated hydrogen bonds molecule is large, whereas in case of intramolecular hydrogen bonding, the peaks are sharp and well defined. They are concentration independent because it is happening within the molecule. No doubt you increase the concentration of the same molecule, the peaks shape or the area of the peaks still remains the same. That's why they are concentration independent, and frequency difference between the free and the associated molecule is smaller because it is the intermolecular hydrogen bonding. I have an example here which shows intermolecular hydrogen bonding, which is a formic acid dimer. I have two formic acid molecules which are forming hydrogen bonding between the oxygen and the hydroxy group of two different molecules. And intramolecular, I have taken orthonitrophenol. Within the molecule, if there is a hydrogen bonding, then we call them as intramolecular hydrogen bonding. So, as I mentioned, if there is a hydrogen bonding, that leads to the increase in the bond length, and increase in the bond length will contribute for loss of or the increase in the bond length will lead to the vibration frequencies which happen at the lower wave number. Hydrogen bond in OH, I am trying to compare with the NH, as oxygen is more electronegative than nitrogen, or the nitrogen is less electronegative than compared to oxygen. Hydrogen bonds in amine is weaker than compared to alcohols. So if it is hydrogen bonding is weaker, then the vibrational frequency will happen at a higher wave number, and if it is hydrogen bonding in OH, if it is stronger, then the vibrational frequency happen at a lower wave number. So hydrogen bonds in amines is weak than that in alcohol, thus the frequency shifts in amines are less drastic. So I have a comparison of amines and alcohols. NH stretch happens at 3500 in dilute solution, and NH stretch at 3300 in condensed phase. And similarly, alcohol, since the hydrogen bonding is very strong in alcohols, the vibrational frequencies are less compared to the NH. It happens at 3400 to 3200, which is intermolecular hydrogen bonding, and in alcohol, in the free alcohol, it is 3600. So I have a range for OH and NH, and generally the NH is having the higher wave numbers except the free alcohol. That's why I have considered 3650 for OH and end up till 3200. And in general, the NH, or since the nitrogen is less electronegative than oxygen, the hydrogen bonding involvement here is less. That's why the wave number is higher, whereas it is vice versa in the OH case. So this was I was supposed to discuss with the factors that influence the vibrational frequencies. So I would like to request you to go through this particular episode, as it is very important and very tricky to understand, and kindly note down your queries if you have any, which we can take up during the doubt clearing session. So I would like to stop here, and thank you all for joining me today for this particular session. Thank you very much.